안녕하세요 여러분, 해리입니다. So in the last video we have finished basic functions, so all those definition of functions, notations, and some types and some properties, right? So today in this video I'm going to talk about transformation. So transformation of functions is very useful when you have to sketch a complicated function. So we always start with what we know, and then we move on to something that we can expand from what we know. So for example, let's say we know how to sketch a specific function like fx. So fx can be something like sine, just sine x, or x squared, or 1 over x, all those basic functions that we've learned. And what if we have to sketch a function which is transformed from here? So something like this. So from here, I'm going to explain the transformation by transformation. So this b here is the horizontal stretch. So this b does the horizontal stretch, and this c here is the horizontal shift. But be careful that when you have something like this, what you have to do first is that you have to change this. You have to factorize this first. So that means this bx minus c, you have to factorize it like this first, okay? And that will be the horizontal shift. And this a here is the vertical stretch. And lastly, this d here is the vertical shift. And of course, there is an order of doing this transformation, and I have seen a lot of students trying to memorize this, but I'll teach a very useful method. So we see that there are a lot of operations inside this transformed function, right? So what we can try is that we can recall what the priority of operations that we know from elementary math. So we first start with the innermost bracket, right? So the bracket. And inside bracket, what do we do first? We do the multiplication first. So that means we can perform horizontal stretch first, and then the horizontal shift, and then vertical stretch, and lastly vertical shift. So this is the possible order that you can use, but in many of the questions and the textbooks, so they group the shift together. So when you have to describe the sequence of the transformation, this is what you should try to do. This is what you should remember. So horizontal shift and the vertical shift. Alright, so then what's the point of doing this? So I recommend you guys to use this when you have to sketch a function. So this is when you have to describe a sequence of transformation, but this I recommend you to use it when you have to sketch a graph. And this is to describe transformations. Okay, so then let's see how we can use this. And before that, one last thing. So we need to learn one notation as well. So for this shift, so all the shifts, so horizontal shift and vertical shift can also be, so we can also use the word translation for describing both horizontal and vertical shift, and then we can also use this vector notation. So that means, so x is the horizontal shift and y is the vertical shift. Okay? And I'll tell you the effects of each transformation now. So for horizontal shift, for this case, let me use my black pen. So horizontal shift is, so we see that B does the horizontal stretch. Oh, sorry, not shift, stretch. So B does the horizontal stretch, and when you have something like Bx, that means a scale factor. So horizontal shift by a scale factor of 1 over B, which means that for every value of x you see in the original function, so what I mean by original function is this original function, you multiply by 1 over b. So an example is something like this. So let's say you have to sketch y equals to sine pi x. So clearly this is a horizontal stretch, right? And this is a horizontal stretch by a scale factor of 1 over pi. So if we have to sketch this, let's just quickly sketch the graph of sine for in its period. So we know that the period of sine is 2 pi. And if we have to sketch this, so what happens is that, as I said, for every value of x you see in the original function, this y equals sine x, we multiply by 1 over pi. So that means nothing changed. So y doesn't change. There's no y effect on y because it's the horizontal stretch, and it becomes, so 0 divided by pi is still 0, pi divided by pi is 1, and 2 pi divided by pi is 2. So this is what you should expect from horizontal stretch. Okay? So this is the first transformation. And the second thing is, so second, we usually go for the horizontal shift. So again, this is for sketching, okay? So horizontal shift. So as I said, if in order to find the horizontal shift unit, unit of the horizontal shift, you have to factorize by this horizontal stretch scale factor first, okay? So that means it's the horizontal shift by c over b unit. So the sign matters, of course. So for example, if it's x minus 2, so let's say bx minus 2, then this means horizontal shift by 2 unit to the right direction, okay? And if it's something like plus, that means 2 unit to the left, Okay, so you can treat that x is always the opposite. So if it's minus, then we move it to the positive side, and if it's plus, we move it to the left side. And also, if it's multiplied, then it's multiplied by the reciprocal. So you can just think that it's always the opposite. So then that's the effect. Okay, and effect. And let's see an example again. So let's use the similar example. So let's say we have sine pi x plus pi. So first we see that this is a horizontal, it has a horizontal stretch by a scale factor of 1 over pi, and it has been translated as well. So it has a horizontal shift, and in order to know the horizontal shift unit, we first have to factorize this. So we can see that horizontal stretch by a scale factor of 1 over pi and 1 unit to the left, right? So from what we have, we know from the previous example, we know the graph of sine pi x, right? Then from this, what we are doing is that we are moving everything to the left by 1 unit. So see, it's 0, 1, 2, right? Then everything moves by 1 unit. So negative 1, 0, and 1. So this 0 becomes negative 1. And when it's 1, it becomes 0. And when it's 2, it becomes 1. So it will look like this. Okay? So that's y equals to sine pi x plus pi. And yeah, that's what we can do. Then the next thing is the vertical stretch. So again, using this vertical stretch with a, right? That means vertical stretch by a scale factor of a. Okay, so y, it's, you just follow what it is. So just that anything with horizontal, so anything with x, it becomes the opposite. So horizontal stretch scale factor, it becomes 1 over b, the reciprocal. And also if it's negative, then it's to the right, and when it's positive, then it's to the left. Okay, so then let's see the effects for this. So what the vertical stretch means is that for every value of y you see in the original function, y equals fx, you multiply by a. Okay, so then let's see another example using this. So now let's say we want to sketch 2 sine pi x plus pi. Okay, so we know this, right? So we can just let this as original function, right? So this original, what I mean by original function is that depends on you. So if you wanna, like, if you want to choose this as the original function, and then if you want to perform this vertical stretch, then yeah, it's absolutely fine to choose this as an original function. But for this one, so since we have to sketch something like this, then it's gonna be much better if we choose y cosine x as the original function. So what I mean by original function is that the function you know. So the function that you can start with, okay? So for this one, so it's a vertical stretch by a scale factor of 2. So that means for every y value we see from here, we double them. So we see that it's 1 and negative 1, right? Then that means what we can do is that, so it doesn't affect the x value, and for every y value you just double it. So 2 and negative 2 and it will be higher, like this, okay? Higher and lower. So note that for horizontal stretch and horizontal shift, it's all about x, okay? And vertical stretch, and the last thing that we're going to do, the vertical shift, it's all about y. So lastly, vertical shift. So from the very first thing, we know that from if we have something like this, then d is the vertical d does the vertical shift, and from here what it means is a vertical shift by d unit. So then for the effect, what we can expect is that, for example, let's say we have a function fx, and if it's plus 1, let's say, then 1 unit upward. Everything moves up by 1 unit. And if you subtract 1, that means 1 unit. So you reduce everything, every y value by 1 unit. Okay? So this is again a shift, and this is a scale factor. So it's a stretch. So stretch and shift, sometimes they can be similar, but as in terms of effect, but they're not the same thing. Okay? This is multiplication, and this is addition or subtraction. So last example could be something like this. So plus pi and plus 1. So that means everything move up by 1 unit. So from the original graph, or the graph that we can start with. Okay, sorry that we don't have much space, but anyway, so we see that all y, so we have two y values here, right? 2 and negative 2 we know. Then everything moves up by 1, so that becomes 3 and that becomes negative 1. So this is something that you should expect to have when you have to sketch this, okay? So just everything moves up by 1 unit. So note that for the shift, the vertical shift, does it affect the x-intercept? Yes, it does, right? And does it affect the y-intercept? Yes, it does. And also for the shift, horizontal shift, does it affect the x-intercept? Yes, it does, right? So from the original function, so the function that we started from, originally we had the x-intercept as 0, 1, and 2. So if we are looking for this region only, okay? This one period. And we see that everything has been shifted to the left by 1 unit. And in fact, the x-intercept changed as well, right? Negative 1 and 0 and 1. So we see that the shift affect the roots. But what about the stretches? Do they affect the roots? So for this one, from here to here, did this stretch affect the roots? And no, it didn't, right? So it doesn't affect the intercept, right? And it's the same for horizontal stretch. But for horizontal stretch, so what I mean by it doesn't affect is that it doesn't affect the y-intercept, but clearly it affects the x-intercept. So you change the value, okay? But yeah, so this horizontal stretch affects the x-intercept because we're changing the x values, but it does not affect the y-intercept. And for vertical stretch, um, it does not affect the x-intercept. Okay. All right. So that's the example, the 4 transformations and examples that we have seen, and let's try an example another example when we have to describe the transformation. So let's say we have something like from something like this. So we have to describe the transformation. So what we can do is that we can try to see how this can be transformed like that. So first, what we can try is that we can use this notation fx, and what we can do is that we try to use fx to make this form. So one by one, so we see that if the input is 2x minus 2, then we will have this, right? And if we multiply by 2 both sides, then we will have this. And lastly, if we add 1, then this is what we will have, right? So from y equals to fx, what it means is that it has been transformed like this, right? So what is it? This is the horizontal stretch, right? By a scale factor of half, right? And this is the horizontal shift, but remember, we have to factorize it first, right? So this one is the horizontal shift by 1 unit to the left, to the right. Okay, and this 2 here is the vertical stretch by a scale factor of 2. And lastly, this one is the vertical shift by 1 unit to 1 unit upward. So then how can we describe this transformation? So again, remember that for describing transformation, we usually group up the translation, so the shifts. So that means for this one, what we can do is that first we have the horizontal stretch, by a scale factor half, and then vertical stretch by a scale factor of 2, and lastly translation by 1 and 1. So remember, this is the x and this is the y, the first notation that we have seen. So this is how we can describe the transformation of this function, okay? And we can also sketch this using what we have. So I'll leave the sketch to you. So you should expect to have a lot steeper, and the y-intercept would be something like this, okay? So this is what you should get for the sketch. So please try sketching by yourself, okay? So that's the first example that we have seen, and I'm going to try some more examples as we have learned several functions, a lot more functions than just exponential. So second example, so that's example 1. Example 2, so let's say we have a rational function like this. Then how can we describe the transformation, and then how can we sketch this? So for this one, it's a bit important, so I will try to sketch with you. well, the previous one is also important, but I think that is easier than this. I think, yeah. But yeah, anyway, so again, let's try what we did just now. So we can start with let's use fx. So we can start with 1 over x, right? And how do we make this? So first, see the effect on x first. So that means if the input is this, then we will have this, right? And then we just simply added 1. So what we can do is that from this we have this. So again, let's just factorize it like this. So how we can describe the transformation is a first stretch, right? But which stretch? Horizontal stretch, because horizontal, it's affecting the x, right? So horizontal is where the x values are located at. So horizontal stretch by a scale factor of half. So remember, it becomes a reciprocal. And second, so let's describe the translation directly. So translation by 2 and 1. Then how do we sketch this? So remember that for sketching, I told you that try to do horizontal stretch, horizontal shift, vertical stretch, and vertical shift, right? For sketching. So then let's do one by one. So horizontal stretch is scale factor of half, right? And then horizontal shift is right to the right by 2. And then vertical shift, there's no vertical shift. Vertical stretch, there's no vertical stretch. And vertical shift is 1 unit of upward. So let's start with 1 over x. So where if we have 1 over x, remember that we have a horizontal asymptote and vertical asymptote. Okay, so first, horizontal shift. Every x value becomes half, but it's very hard to show this effect on the graph because we don't have a specific point. So what we can do instead is that so for any point, let's say we have 1 here, then just show that now half becomes 1. And that makes perfect sense, right? Because horizontal stretch by half scale factor means this, right? So when x equals to 1, then y becomes half. Oops. Wait a second. Oh, sorry. So when x becomes half, it becomes 1. Yeah. So, well, this one we can also interpret this as vertical stretch of half of scale factor. That's why. So, but we are going to use horizontal stretch for this one. Okay. So first, what we can do is that, so just indicate 1 point. So when it's half, it becomes 1. And everything is the same. So the horizontal stretch and vertical stretch, horizontal asymptote and vertical asymptote is the same. And now what we do is that we everything to the right by 2 unit. So what I mean by everything is that every x value, right? So remember we had a vertical asymptote, x equals to 0, and this is x value, right? So every x value, even the asymptote, is affected. So now we have the vertical asymptote as x equals to 2 and still doesn't affect y. So, and this when it's so we add up by 2, so that's 5/2 and it's 1. And now note that we have a y-intercept, right? Because this, while this has been shifted by 2 units, it crosses with y-axis. And how do we find this y-intercept? Well, it's simple. So what we have is, so we have to track with what we are sketching. So this is what we have sketched, right? So if we put 5/2, that means it's 5, and 5 minus 4, 1. So that's why this point makes sense, right? And also for the y-intercept is when x equals to 0. So that should be negative 1/4. And lastly, everything upward by 1 unit. But what everything? X? No. Y, because it's the vertical shift, right? So we had a horizontal asymptote, y equals to 0, but now the horizontal asymptote becomes y equals to 1. And then we have a vertical asymptote, x equals to 2, and what about the intercept? Add up by 1, right? So this is the y-intercept, so that means we have the intercept at 3/4, right? And also, while we shift everything up, we may have a x-intercept. So this is what we have. And in order to find x-intercept, y equals to 0, right? So that means minus 1 equals to 1 over 2x minus 4. So 2x minus 4 equals to negative 1. That means so x-intercept equals to 2/3. So this is what we have for this side, and then this will be simply just this, okay? So this is how we can sketch more complicated function from what we have using transformation, okay? So this is starting. So this is the effect of 1, and this is the effect of 2, and this is the effect of 4, okay? So this is an example, and one more example that we are going to see. So I'm trying a lot of examples so that you guys can get more familiar with sketching. Because the reason why I'm keep emphasizing on sketching is because you have to sketch a lot especially for calculus. So calculus, like for example in integration. So, and also you have to sketch a lot in like other topics like trigonometry, functions, this chapter, and yeah. So please get familiar with sketching. So now first we want to describe the transformation, and then we want to, from this we want to describe the transformation, and we are going to sketch it. So okay, note that the starting function is defined like this. So we have to start from here. So function is given like as, so this is the given function, negative root x, right? And what we did is that first we have a horizontal shift, right? And then we have a vertical shift. So no stretch for this case. So very simple, right? Just translation by 3/1. Okay, So how do we sketch this? So I'm pretty sure you all know how to sketch this because that looks like that. So one by one, so we can perform this horizontal stretch first. So keep tracking what you're sketching, okay? So everything moved to the right by 3 units. Then this is what you should expect, right? And then everything move up by 1 unit. So for this one, we see that we have a root, right? Then we have to find the root, right? The x-intercept. So how do we find the root? Well, shouldn't be that difficult. So x-intercept means y equals to 0. So negative root x minus 3 equals to negative 1. Be careful with squaring because sometimes if you square it in a wrong manner, you may have a wrong answer. So anyway, so this is how we can find the root. So that's a sketch of this irrational function, okay? So we have seen 3 examples with the functions that we learned. Now we are going to see some special examples of stretches. So reflection. So mainly there are 2 reflections. So one is the reflection over the y-axis. So when you have a function like this and when you have to sketch this. So first I'll just explain using a example. So let's say we have a function like this, let's say. So where this is 2 and this is negative 2, negative 1, and that let's say 2, and let's say negative 3, and 2, so 5 and 4. So we have 4 points. Like this. Alright, so what we are going to do is that we're going to sketch this. So we see that negative 1, that means a horizontal stretch by a scale factor negative 1. So does it affect y? No, it doesn't. It's just affecting the x, right? So that means, so when we apply this, we will have this, right? And we will have this. So we have these 4 points. And if we sketch this, if we sketch the graph based on these information, new information, what we will have is that when x equals to negative 2, we will have a value of 4, which is that, right? And when f equals to negative x equals to negative 1, we will have a value of 5, right? And then still we have the origin, and when x equals to 1, we have value of negative 3. And lastly, when x equals to 2, we have a value 2 here. So you see that it's just the graph is just reflected around the y-axis, okay? based on the y-axis. So that's one of the reflection. So the second thing should be very simple. I'm pretty sure you have seen this a lot of time. Also, when we have a function like this, and we have to sketch this. So this means reflected in the x-axis, and this is reflected in the y-axis. So for example, a very easy quadratic function. So we all know that y equals to x squared looks like this. Then what about y equals to negative x squared? It's a shape of unhappy face, right? And also for any other quadratics that we learned, this will be just flipped, right? Reflected in the x-axis. So I just explained using quadratics, but it only works, it works for some other functions, any other functions as well. So any like trigonometric or log exponential, so on. Okay, so we have learned two reflections, and before we stop, so one quick tip for rational function. So for if you're in SL students, you will have to learn. So for rational functions, you just need to learn horizontal asymptotes and vertical asymptotes. But some questions, you will have something like this. So in this form, then how can we sketch this? Because it's not, so remember, so we know, even if you want to use transformation, you start with what you know, right? But it's not gonna be easy for you to use this to make this, right? So that means it's very hard to describe the transformation if the graph is like this, right? So for this case, what can we do? So, no, not example, so rational. So for example, if we have this, what we can do is that we can do long division. The reason why we're doing long division is because we want to make this in the form of this. Okay? How? So I'm pretty sure you have already learned long division from MYP and GCSE. So 3x minus 6. Then subtract plus, so that will be 5, right? So that means this can be written as 3 plus 5 over x minus 2. And it's done. Why? Because that's the horizontal shift by 2 units to the right. And this is, or you can either describe this as vertical shift by 5, or you can put it like this to make it as a horizontal shift. But for this one, of course, it's going to be easier to use vertical stretch and a vertical shift of 3 units upward. So if you have this, then you can apply what we have learned, and it's going to be very simple to sketch. But one last thing. So what if we have a higher coefficient in the denominator? Something like this. Okay, I'll just make it a bit more nasty. Then again, it's the same. 1/3, right? 1/3, that means it's x plus 7/3. So if you subtract it, that's 2 over 3. So this, you can write it as 1/3 the quotient plus the remainder over 3x plus 7, which is this is what you can do. Okay, and then it's gonna be, I have done all the job for you, right? So this is just a transformation that we've learned, so it should be fine for you. Okay, so that's it for SL students functions with transformation. And for HO students, you need to do a bit more. So we're almost, to be honest, we have covered almost everything, but we just need to do a bit more on rational. So you have to learn something called the oblique asymptote, where it's no longer vertical or horizontal. So asymptote as in function, another function. SL students, you're done with transformation. So in the SL transformation, we have seen almost everything for HO as well. So the basic transformation like stretches and shifts, they are still the same for HO as well. For HO students, we need to learn mainly two more. So we're going to learn transformation involving modulus. And then after this, I'll also explain the reciprocal function. So after these two, then you're done with the HO syllabus too. So modulus function is an example of piecewise function. So we know that, so modulus, we can write it as x when x is greater or equals to 0, and negative x when x is less than 0. Because, for example, let's say we have -1 in the modulus symbol, then what do we have? We have 1, right? And if we have just a positive value, we still have positive value. And when we have 0, we have 0. So based on this, when the value is negative, then we put negative sign in front of the original value. Not the original value, but the input. So we put negative sign on the input so that we have 1, like this. And if the input is already positive value, then we just have the input itself. And again, 0 and 0. So transformation involving modulus, so basically we have two types. So the first type is when we have the modulus on x values. So it's related to values horizontally. So whenever, okay, so let's say we have a function like this, and then let's say we want to sketch this, then this is an example of even function. Why? Because using the inverse modulus property, this will always the same as this. This will always the same as this. So what we can interpret graphically is that you can try to think that you're basically copying everything on the right of the y-axis to the left. So for example, let's say you have a graph like this. So this is y equals fx. Then if you want to sketch y equals to f modulus x, so what we can think is that for every negative value here, we'll have the value of the positive x values, x input, according to this, right? So this is what you should expect. For example, so if you don't understand, so let's say this is 1 and 1, and this is -1 with half, let's say. So in the original function, we have these 2 points, right? But in the modulus, so every input has modulus sign, right? So modulus of 1 is still 1, which is the same. But modulus of -1 will be f1, right? So the modulus value, so the negative value inside the modulus will become positive, and it will be 1. So we see that the value has been copied. Okay, so this is how we can sketch the modulus function with, transformation involving modulus on horizontally. Then what about the second case where you have the original function and then you have to sketch the entire thing modulus? So again, what it means is that when you have a negative value, so always remember that modulus, for a modulus symbol, what it's trying to do is that whenever you have a negative value inside, you just convert that to positive value. So what you can think is that if you have a function like this, let's say A, B, and C, then, and let's say this is just fx, then the modulus of this would be this. So every negative value of fx becomes positive. Okay, so just flip everything above the x-axis. Okay, flip everything above the x-axis. Okay, so that's it for the transformation involving modulus. But of course, the real life examples, the actual practices will be more difficult. So you will not be asked to do like just one modulus. Very likely you will have some transformation with modulus. So like other transformations, so like shifts and stretches. But don't worry, we're going to do those. I'm going to post some of those examples on the sample test, and then I'll tell you how to solve those problems. So let's move to the reciprocal functions. What we're going to move on is that we're going to move on to reciprocal functions. So that's it for transformation, okay? So now we're going to move on to reciprocal functions. And what it means by reciprocal function is that when you have a function like this, so starting function, and what you're trying to sketch is you're going to sketch a reciprocal of the function, so 1 over that function. Then how do we do this? So some of the properties that you can remember, so I don't really recommend you to like memorize these properties, because to be honest, it's much better if you can understand why we have such properties and then apply directly when you have a question. But if you really want to memorize it, then I will not stop you. So first, for the original function, if we have x-intercepts, then for the reciprocal function, those x-intercepts become the vertical asymptotes. And I'll explain this. Well, it's very simple, easy to explain. So let's say x1 is a root of fx. That means fx1 equals to 0, right? Then in the reciprocal function, what does it become? 1 over fx1, which is 1 over 0. And this is undefined, right? So that means x1 becomes the vertical asymptotes. Okay, so all x-intercepts in the starting function will become the asymptotes in the reciprocal functions. Okay, and second, so in the original function, if the y value diverges, so what it means by diverges is that it just goes on forever. So either in a positive direction or negative direction. So for example, what I mean by diverging is that something like this. So if we have a cubic function like this, y equals to x cubed, we see that the y value goes to the infinity, right? Positive infinity when x tends to positive infinity. And the y value tends to negative infinity when x tends to negative infinity, right? So when the y value diverges, then for the reciprocal function, it converges to 0. So what it means by converges is that something like something like this. The thing that we learned. So yeah, something like this. So remember this exponential function, the graph of this exponential function. So we can see that as the x value goes to negative infinity, then y value gets smaller and smaller and smaller and tends to 1, right? And it doesn't go below 1, but it just becomes 1. Not becomes it. So we say that it converges to 1. So converge means that it does not equal. So converge doesn't mean it eventually becomes something. No. So this means that it approaches to 0. Okay. And lastly, for every y value in the starting function, then for the reciprocal function, they all become reciprocals. Because we see that every y value here, we put reciprocal, right? So that means every y value for the original function, the starting function, it just becomes, they become reciprocals. Okay? So I'll try an example with you. Let's say we have a very simple quadratic function like this. So so we don't have an asymptote yet. So -2, -1, and then 2. So this is how the graph would look like. And let's say we want to find this vertex as well. So we can directly find the vertex by using this, right? So that this tells us the x coordinate of the vertex, right? Using completing the square. But you can just directly complete the square, so it's not that difficult. So this is what we will have. So that means at 1.5, negative 1.5, the y value is negative 1/4. So that's the vertex, right? So now we have every information of this quadratic equation. And now what we want to sketch is that we want to sketch the reciprocal of this. So what we can do is that, so note that, so the main idea for reciprocal function is that all y values becomes a reciprocal. So here when x equals to negative 2, y equals to 0, right? That means when x equals to negative 2, y is undefined because it's 1 over 0, and it's the same for negative 1. Then what about when x equals to negative 1.5? Then this vertex, this negative 1/4, will be, again, it will be so you take the reciprocal here as well, so it will become negative 4. Okay? And note that, so see that when x tends to negative infinity, y gets positive infinity, right? Then positive infinity, then it becomes 0. It converges to 0, right? And then when it approaches to negative 2, it will be very large. So it will look like this. And again, this would look like this, because as it approaches to negative 2, it will tend to infinity, right? Okay, if you don't understand why it tends to infinity like this, so the more close the value, for x, the more close it is to negative 2, this value, this original value, will be very close to 0. So that means very small number, right? It will be very small number. As you can see, it's the y value will be very small. But what if you take the reciprocal to that very small value? So for example, let's say that small value is like, for example, 0.01. Then if you take the reciprocal, it becomes 100. And if it gets closer to 0, so something like 0.001, and if you take the reciprocal, it becomes 1,000, 10,000, and yeah, it becomes really large. That's why. But note that this is at the negative value, so it will be negatively large. And it's the same for this. It will become negatively large. And lastly, the y-intercept of the original function, the starting function is 2. Then in the reciprocal, it will become negative half. Not negative. It will become half. And then this is what you should expect. So see that it's again tending to positive infinity. Then if you take the reciprocal to the positive infinity, that means it will be very small, right? So for example, let's say 1,000, then reciprocal of 1,000 is 0.001, and something like 10 to the 7, then it's 1 over 10 to the 7, so it's going to be even smaller. Okay, so it will converges to 0. So this is how we can sketch the reciprocal of a given function. And this should not be hard, but so something like this can be a bit difficult. So let me just quickly make a question. Let's say you have something like this. So I know that it looks very disgusting. So let's say negative 2, and this is half, and this is negative 1.5, and this is negative 3. And what else do we need? We need this, so let's say 3, and okay, so sorry, so since we're learning function, let's not consider this. So let's say you have so you have something like this. Okay, so this is where negative 2 is, and then you have like 5 here. So the equation is not given, and you're supposed to sketch this. And how can we sketch this? So unlike the previous case, we have some straight lines, right? And there you may have a graph like this. For example, for let's say velocity versus time graph, right? So there could be a constant speed, right, or changing speed. So, yeah, let's try to sketch the reciprocal of this. So first, what we can start with is that for every x-intercept, make them into the asymptotes. And for every point that you know, find the take the reciprocal. So at -2, it's half, right? That means in the reciprocal function, at -2, it will be 2, right? And then also, this -2 value of -2, it will be -1/2, right? And is there anything else? Oh, so let's call this this point as 2 and -2. So at 2, it's also -1/2, right? And this is what you would so this is the first job that we do, and then we sketch one by one. So first, before -3, the y values tends to infinity, right? That means it converges to 0. And then as it approaches to -3, it will tend to infinity. But negative, they're all negative, right? So they're still negative. And for this part, so here, so as it's close to -3, then in the reciprocal, it will be positive infinity. And then it reaches this point, and also it goes back. And one thing is that we have a linear, right? What happens if we take a reciprocal of the linear? Is it still the linear? No, it's a curve. And why? You can just use the example of y equals to x and y equals to 1 over x. So y equals to x and y equals to 1 over x is a reciprocal relationship, right? And do you have a straight line in y equals to 1 over x? No, you have a curve, right? So it's the same idea. So even this is a linear, we have a curve like this. And it's the same for this one. So, but for this, still it's the flat line. Oh, okay, so for this one, let's call this as -1. So -1. So this is what you will have. And the same, so it's close to 0. That means it's infinity, right? And since it's negative value, so negative infinity. So this is what you will have. And lastly, for this one, so from 2 to 5 first, so it's still on the negative side, and so for the original function, it tends to 0, right? So that means it tends to negative infinity. And lastly, we have this. So this is what you can sketch for the reciprocal of a weird graph, let's say. So for those students who want to revise this again, I'll just quickly sketch it again. So yep, so this is what you can try to try by yourself later, okay? So that's it for the reciprocal.